Our next topic is called crashing. Crashing means paying overtime to finish an activity early. There's lots of reasons why we might need to finish an activity early. Very often that's associated with finishing the project early. If we want to finish the project early, in other words, then we're going to need to expedite an activity that's on the critical path, maybe more than one activity on the critical path. Or sometimes we might get behind and we have to expedite another activity in order to get caught up. Sometimes we might even need to expedite an activity that's not a critical activity. Perhaps that there's a resource required to perform that activity, and that resource is needed on some other project in our company, so we need to get that resource done early. So we either need to expedite that activity or maybe expedite a predecessor activity to that activity so that that activity can start earlier. If our objective is to get the project done early and we're in the early stages of the project, then chances are if we crash any activity on the critical path, it will improve the due date or the complete date of our entire project. So that raises the question, which activity should I crash? Which activity should I expedite? To answer that question, we probably want to look at the cost of crashing the different activities. Usually if we crash an activity, we want to get it done quicker, we're going to have to pay a premium to make that happen. That might be overtime, that might be some bonus or some type of premium we're paying to a contractor. But generally, if you want to get it done sooner, it's going to cost you. Right? So what we can do is we can look at those premiums on a per day, per hour, per week basis. For example, if we are doing all our activity time estimates in days, we would probably want to use days, so we would want to convert the cost to crash any particular activity into a cost per day. So to crash this particular activity, it's going to cost me X dollars per day of time that I want to save. The name for that is the marginal crash cost, or the marginal cost of crashing. And of course, if we've got a choice between crashing several different activities, we would probably want to select the one with the lowest marginal crash cost. The one that's going to be the cheapest, or the one with the lowest premium, is the one that we would want to crash, or the one that we would want to crash first. So let's talk a little bit about how we might want to do that. Let's go back to the original project that we looked at. Remember that the critical path on this project is A, B, E, G, I, the path in the middle. Recall that the critical path on that project was 20 days. So, again, to select the resource to crash, you want to pick the one with the lowest marginal crash cost. If crashing that first resource doesn't give you all the time that you need, maybe the activity has an estimate of 4 days, and the most we can possibly crash it is 1 day, so we can get it down to 3 days. But if we want to shave 5 days off our project, we're going to need to crash some other activities too. So we would select them in order, beginning with the one with the lowest marginal crash cost, then moving to the next lowest, and so on. You do have to watch sometimes that when you're crashing that your critical path doesn't shift. You may crush your critical path so much that your critical path goes someplace else. But let's assume that you've got that under control. You understand that, and your main consideration right now is just figuring out which activities do I want to crash. Okay, so here, going back to our example, what I've done here is I've listed some sort of fictitious additional data here. Got the normal activity times for all the activities in the project, and I just took those off the activity on node diagram that we were looking at. And let's assume that, for example, for activity A, normally it's going to cost me $70 to get that activity done. To get that activity done in a normal amount of time of 3 days. I can crash that activity down to 2 days. So I can shave a day off that activity time. If I do that, the total cost to do the activity is going to be $100. So it's going to cost me $30 more if I do it in 2 days. And then I've just kind of made a note here in this column, the max time column, that what I'm doing is I'm shaving off that 1 day. All right, and I'm assuming that's the best I can do. So the difference between the normal time and the crash time is this max time, and we assume that this crash time is the best we can do. And then I've also computed my marginal crash cost, and to get my marginal crash cost, I look at the difference in cost. So for activity A, it would be 100 minus 70, or 30, divided by the amount of time that I save. So in this case, I save 1 day, so it's $30 per day, my marginal crash costs. So I can compute my marginal crash costs for each one of my activities, and just for convenience, I also compute my maximum amount of time for each one of those activities. Let's say that I want to get the project done 2 days earlier than the original time. So I've got the same data here from the previous slide. How do I want to do that? Well, the best way to do that is going to be to start with the activity with the lowest marginal crashing cost. Or the cheapest way to do it, I should say, is going to be to start with the activity with the lowest marginal crashing cost. Now, if I look at the MCC column, I can see that that is this activity here, activity I, with a marginal crash cost of $20. However, the max time on that is only 1 day, so that's going to give me 1 day, right? But I still need 1 more day. So now what do? Well, I look for the next cheapest marginal crash cost. That's $28. That's activity E. I can crash that activity up to 2 days, but I only need 1 day. So I'm just going to reduce that activity by 1 day to get my 2 days. So the total is going to cost me $20 to get my 1 day here, and $28 to get an additional day here. The total then is going to be $48 to expedite 2 days out of the project. Remember, this $28 is the cost for 1 day. The marginal crash cost is the cost per day. Let's talk about several other concepts that can improve our ability to manage projects. There's a couple concepts that are part of what's called the critical chain method. The critical chain method was developed by Dr. Goldratt, the same person who wrote The Goal, and you'll probably see some concepts from The Goal sort of at work here as well. One thing that the critical chain method recognizes is that conventionally the departments or whoever is giving the activity time estimates usually will tend to inflate those estimates a little bit, build in a little bit of buffer, a little bit of slack into each one of those estimates. Let's understand exactly what's going on with these activity time estimates. A lot of times activity times, if we look at the actual times it takes to get activities done, follow a distribution that's skewed. So it's not our symmetrical normal distribution like we've talked about quite a bit in the class, but it's often a distribution that has, a bit of a long tail off to the right. So the most likely time might be, let's say, 4 days. A really optimistic time might be 2 days. But on the pessimistic side, this thing could extend on, quite a bit longer than 4 days. So if I'm a department manager and you're a project manager and you've asked me to give you a activity time estimate for this activity, what time would I be most likely to give you? Well, I might realize that if it takes me longer than the time I give you, I'm probably going to get yelled at, and maybe some other bad things are going to happen to me. And I understand that this most likely time here of 4 days, there's about a 50% chance that I'm going to get it done within the most likely time, and there's about a 50% chance it's going to take longer than the most likely time. That's the properties of the distribution. Let's say that I'm kind of conservative and I'm a little bit risk averse, like most people when it comes to their careers, and I want to give you a time that I'm 85% sure I can hit. So in other words, I've got to find a value that encompasses 85% of the area under the curve. Well, because this distribution kind of starts to flatten out here, because we recognize that the activity could really go on quite a long time. I've got to get pretty far out to get to a point where I can cover 85% of the observations. I've got to get probably way out here to get something that I'm not confident that I can hit, and that looks to me like probably at least 7, maybe 8 days. So I'm really building in quite a bit of extra padding here. Let's just say it's 7 days, but that's the time that I'm probably going to give you, even though 50% of the time I'm going to be able to get it done in 4 days or less. And that is sort of what we've got going on here. Here we've got a project that consists of 5 different activities, activity A through activity E. And if we did what we just talked about, we went and we got activity estimates from a bunch of risk-averse managers, and they all padded them a little bit. They might all give us estimates that look like what we've got here, and they've all kind of padded. Build in some extra time. I'm kind of shading the extra time there for activity A, and everybody's done that. The person who's responsible for activity B has done that, and so on. So what we do, according to the critical path method, is we add up together all those activity times, and that gives us the completion time for our project out here. What's the problem with that? Well, usually, even if these activities get done earlier, the people that are responsible for those activities don't typically report the earlier completions. If you always reported your earlier completions, then people would start to wonder, well, why are you giving me such long times all the time, right? Or a lot of times if we give people a completion date with a lot of kind of extra built into it, we wind up delaying the start on the activity. In either case, basically what we're doing is we're wasting the buffer. We're wasting the slack. You built some buffer in here. You got the activity done early, but you didn't tell anybody about it, or you procrastinated starting the activity, so you wasted this buffer. So if you waste the buffer winds up not really doing you any good. So the critical chain approach is to do whatever you can do to get reasonable activity estimates from individuals, but then you buffer at the project level. How do you get those reasonable activity estimates from the individuals? Well, you probably have to make it understood to individuals and to top management that you understand that a large percent of the time, maybe 50% of the time, the actual activity is going to take longer than the estimate, but that's okay because you've got this project buffer, right? So we expect that we're going to eat into some of this project buffer. We're going to need to use this project buffer because chances are at least one of these activities, if we really do get accurate activity estimates from our managers, some of these activities are going to take longer than estimated. But if we put the buffer here at the project level, we tend not to waste the buffer. Okay, the other aspect of the critical chain method that the text discusses and that we should probably try to shed a little bit more light on is the idea of feeder buffers. And the idea of feeder buffers is based on the fact that you've got your critical path, and just as kind of a reminder, here's our critical path through our project. Things that happen off the critical path, though, can delay the critical path. Like what happens if activity D gets really, really seriously delayed, then it could also delay the start of activity G, right? And since G is a critical activity, if G gets delayed, the project is going to get delayed. So what we can do is we can buffer any activity that feeds the critical path, and here activity D would be such an activity. One way we might do that is we might build in a dummy activity of, let's just say, 2 days here, and that's going to force activity D to finish 2 days before G is scheduled to begin. So it's going to give us a 2-day buffer here, really decrease the probability that anything going wrong on D is going to impact G. Even if something goes wrong on D, as long as we can get it resolved within 2 days, we're going to be okay, and it's not going to have an impact on activity G. Let's discuss the role of resources in projects. I've got another project for you. Let's say that the college thing doesn't work out so well for you, and you get your degree, but you can't get a job and you fall into a life of crime. But you become pretty good at robbing jewelry stores, and you hook up with a couple other people, and you've got this one particular heist that you're thinking about doing. You want to rob a jewelry store, you want to hit the jewel safe and the office safe, and you've got two accomplices, and each one of these accomplices has a special skill, and so do you. There's a safe cracker, and there's an alarm cracker, and there's a driver. And here's the project. You've had this class, you did pretty well, and you decided to treat this jewelry store heist like a project. So you can see that here's the different activities that have to be done in the project, and you can also see, based on the color coding, who's responsible for the different activities. And let's say that you've kind of cased out this jewelry store, and you realize that the police drive by every 50 minutes. So the question is, can you get this project done in 50 minutes? So I'd suggest you just pause the presentation for a minute, think about the critical path and other things that we've talked about, and figure out whether or not you can do it. Okay, well, you might have added up the length of the two different paths, and if you did that, you'd see that this path down here is the longer path, and this path takes 48 minutes. This path here is, let's see, 20 plus 14 is 44 minutes. Our critical path is 48. And 48 is less than 50, so we should be able to get the project done. But let's kind of think about what happens here. Here I've just tried to diagram out minute by minute what might happen in this project. So we start activity A, and it takes 20 minutes, so we finish that up in minute 20, at which time activities B and activity D can start. So activity B then would begin at time 21 and go to time 27. Activity D would begin at time 21 and go to time 24. And moving on here, we can start activity C at time 28, right? Actually, that's not right. Because think about what's required for activity C to start. Not only does activity B have to finish, but something else has to happen. The same resource that does activity D also does activity C. So the critical path here is not really telling us the whole story. And activity D is going to be busy until time 34. So activity C can't start until time 35. And it takes 35, 36, 37, 38, 39, 40, 41. It goes to time 41, which means this activity can't start till time 42. And if it starts at time 42, there's no way it can finish up by time 50 if it's a 10-minute activity, so you're going to go to jail. So what we're seeing here is the importance of taking into account the individual resources that are going to perform these activities. It's infeasible for us to get this project done in 50 minutes because of the individual resources that are needed. What we've got here is an example of what is called resource contention. We started out talking about the project triad, the fact that very few projects get done on time, on budget, and within specifications. However, if you understand and you practice the principles that we've talked about, your chances of getting that done will improve greatly.